All right, so these are some basic survival tips. This is a guideline to how to figure out these problems in electrochemistry. Do not let it trap you into the steps. All electrochemistry problems are just science math problems. So basically, you get the units right, understand the underlying properties, the physics of it, the chemistry of it, and you'll be able to get the problems right even if you don't use these steps. Okay? And also, we may approach things from different ways. Not every problem is exactly these steps in this order perfectly. Okay? However, this will give you a good start. It'll give you a good foundation. Step one, write the two half reactions and their standard potentials. If you choose a half reaction for which you cannot find E naught, then find another way to write the reaction. This may involve flipping things. This may involve putting reactions together to get the half reaction. This can involve a few different things, okay? But you need at least two half reactions to complete a cell. Number two, write a Nernst equation for the net reaction. Put in all the known quantities. If all is well, there will be only one unknown in the equation to solve. And that'll be a straightforward electrochemical problem, right? Notice the Nernst equation has pretty much every factor that you would typically deal with in one of these situations. So the Nernst equation is a great place to start. Number three, solve for the unknown concentration and use that concentration to solve the chemical equilibrium problem that was originally opposed. I think that's pretty straightforward, actually. There's not much more I can put on there, is it? All right. Okay, so what would happen if you analyze a very complicated cell? So we have a cell here, 1411, measures the formation constant, Kf, of this mercury EDTA. The right-hand compartment contains 0.5 millimole of mercury 2+, 2 millimole of EDTA, and it's in 0.1 liter of buffered to 6 pH. And so this is the condition of that cell right there, if you're curious. Notice that this is the volumes with the concentrations. Okay? All right. So that would give you these values. The voltage going across here is 0.342 volts. Let's find the value of Kf for that mercury EDTA. So you go through your steps. Step one, the left half cell right here, that's a standard hydrogen electrode, right? An SHE. So you'd state, you don't need to do anything else because that's standard, right? That's 0. That's that standard half reaction for hydrogen going H2, and that would be 0 for the E, right? Fantastic. So in your right half cell, your mercury is going to have 2 oxidation states. So we need to write the half reaction for this. We have the mercury liquid here, mercury 2+ taking on 2 electrons to give us mercury liquid. By the way, the mercury liquid would be down here, if you're curious. You'd have to have a platinum electrode, because mercury obviously would not form a good electrode. It's not solid. It's a liquid, right? All right. That E naught plus is going to be 0.852. So we write the Nernst equation for that right there. Notice this is room temperature, so you can use the simplified version. We get the 2 from this 2 electrons here, right? Okay. Notice that the E plus has the E naught here and 1 over the mercury 2+. Why is this 1 up here? log of, well, it's the reaction quotient in here, right? So it should have been product of a reactant. Why is that 1 then? Because if it's a pure liquid or solid, what happens? It goes to 1, right? It's unity. Don't forget that. It's very easy for people to forget that. And because it's, you know, it's back in the past. You're on like, Gen Chem 2. I don't need that stuff anymore. But still using it, aren't we? All right. Again, though, that's not the only reaction going on there, right? We also have another half reaction. The other half reaction being the formation, the KF that we're trying to find, isn't it? And so that would be the mercury 2 plus binding to the EDTA, the one that's going to bind to the strongest, the one that's going to be the vast majority of binding is going to be the Y4 minus form. And that will give us our KF for that equilibrium, which would be the formation of this complex, the HgY2 minus, right? Gamma 2 minus if you want. All right, so we would assume this KF is pretty large because pretty much all the EDTA KFs are large, right? And the mercury one, if you remember, that should be pretty damn large too. So we're going to assume in this, to make the math easier, that virtually all of the Hg2 plus has reacted to form the mercury complex with EDTA. So the concentration of your mercury complex with EDTA is going to be the concentration of your mercury, essentially, which is that 0.5 millimoles for 100 milliliters, which would be 0.005 molarity, right? Again, that's the volumes here, and that's that concentration, well, moles, right there, right? Okay, so we have a molarity of that complex, right? Notice we're back to an equilibrium problem that we can deal with, aren't we? Okay, so again, the EDTA is going to be that 0.0150 molarity of EDTA. And what we'll have is a small unknown concentration of the mercury that's free in the solution. That we pretty much don't have to worry about. Notice the concentration here for the EDTA, we just subtract what we used from what we started with, right? So we started with 0.2 minus the 0.5 from here, the mercury, and then divide it by the volume, right? That gives us the molarity. Okay. So KFs, well, those are equilibrium constants, right? So they're always going to have an equilibrium constant expression, aren't they? And that's just the products of reactants because it's a nice 1-to-1 ratio here, like pretty much all the EDTA ones are. This is just going to be the powers of 1 everywhere, right? Don't forget, because we're doing EDTA, we're going to have the Y4 minus form, right? So we're going to have a mole fraction that we have to put in. Because not all of the EDTA is going to be in the Y4 minus form, is it? Especially not at pH 6. See that? pH 6, most of it won't be in the Y4 minus form, will it? So we will have to add that in. That's that alpha, Y4 minus here. It's multiplied by the EDTA concentration. That will give us the amount of Y4 minus in the solution, right? The mercury, that's going to be a very small value that we're going to end up having to solve for, right? And then we have the mercury complex, which is what we figured out up here. Essentially all of the mercury is going to be in that form, right? And whatever's not is such a small amount we can ignore it in terms of minus or plus X, right? Okay. Again, this EDTA right here, that's the formal concentration. Don't forget this one right here would not be that formal concentration, right? That's the fraction in the Y4 minus form. Okay, Does everybody know where to get this mole fraction of Y4 minus? You remember you had that table at 25 degrees Celsius. The alpha for Y4 minus would be at each pH. So you'd get that table, you'd look up 6. That would give you that alpha. Okay. Mole fraction. Fantastic. So you plug these things in. We're going to have to find the Hg2 plus concentration to find the Kf, aren't we? And the Kf is the answer we want. Well, we have something that's related to that, don't we? We have a Nernst equation. We have voltages and we have Nernst equation. So remember, your E value was 0.342, right? Your E minus was, well, 0, because that was an SHE, right? No problem. And then you also have that mercury going to mercury liquid. Remember that one? So you plug that into the overall Nernst equation for the cell, the net cell reaction. Remember that equation? It only had one variable, didn't it? Which happens to be the mercury 2 plus concentration we want. And so we'll solve for this concentration right here. That will give us 5.7 times 10 to the negative 18. Notice the 0.7 is actually a uncertain variable. Our significant figures actually end at 1, 8, and then the 5. 3 sig figs. Because this is an exponential. Which is how we have to get this out of here, right? Okay, so once we have the value of mercury 2 plus, we can put it into our Kf expression down here. All these other ones were ones we've already figured out, and this one from the table. We plug them all in, we do the math, we get 3 times 10 to the 21st. We go, yeah, that looks about like a Kf for EDTA binding to mercury. And we got our answer, didn't we? Okay. It is very interesting to note, by the way, that the mixture of EDTA in this problem plus the mercury EDTA in your cathode is actually a sort of mercuric ion buffer. Like a buffer would normally be for H+, right? Instead, this is a buffer for a metal ion, right? And that buffer actually fixes your concentration of the mercury in that cell. So that actually determines your voltage, that buffer solution. You could put in then different buffers in here, right? Instead of EDTA, you could use a different keylining agent that has a different Kf and generate different voltages. Isn't that kind of cool? Yeah. Come on, that's amazing. You gotta love it. A little side note to this, by the way, I did not do much publication work in electrochemistry. If there was one part that, like every other part of analytical chemistry that we do, I've done real publications in it, I've done lawsuits using it, I've done all sorts of stuff. This is the only one that I've never done a publication or lawsuit or anything really in my entire post courses that I've only ever done essentially this level, which is unfortunate actually. There's actually some really cool stuff. I did work with a group that does batteries, but I never actually got to play with their battery concentrations and stuff. Just sad. So let's talk about the biochemistry uses of E0. Obviously, you kind of already know this because you guys have been through the biochemistry course, and I have a whole part of this, right? Like 10 slides, probably about half an hour worth of stuff. So whenever we have an H+ that appears in a redox reaction, whenever reactants or products are acids or bases, these reduction potentials are always going to be pH dependent. Notice the pH scale literally has a redox potential to it, doesn't it? Because you're concentrating positive ions. That makes sense to you? And in fact, you already kind of knew this because the entire citric acid cycle harvests its energy using a pH or H plus concentration battery, essentially, doesn't it? That generates the ATP. Everybody okay with that idea? So the pH inside a plant or animal is usually about approximately 7. Redox potentials that apply at pH 0 are obviously not appropriate for that, right? The standard potential for a redox reaction is going to be defined for a galvanic cell in which all activities are unity. Remember, that's the standard potential that we were looking at on all those tables, is that all activities are unity. 1, right? The formal potential is the reduction potential that applies under a specific set of conditions. So the biochemistry version of the formal potential is at pH 7, which is denoted by E0 prime. So notice we have a modified standard. And what is that modified standard? Well, it's for the activities at pH 7, right? Okay. Here's a table of these, by the way, and how they change. So these are the E0s. These would be unity at 25 degrees Celsius, right? These ones right here would be at pH 7. They're for physiological conditions. So they're the E0 prime. And notice how different they are. Not all of them. Some of them are the exact same. But every now and then, you get one that's very different, right? Notice here, this is kind of an interesting one. Cytochrome C with iron 3 plus versus 2 plus. There's the physiological conditions for it. Ooh, note the SHE under physiological conditions would obviously be very different, right? Because that one depended on H plus concentration. So us changing the H plus concentration means we've essentially made a concentration battery if we were to compare the two, right? Just like a citric acid cycle would. So this is the Nernst equation for half reactions again. This is just the generalized setup whenever we're talking about these systems with H+. Okay. And so notice that here we have B to the concentration of B, H plus is a product, and it has a coefficient, which would be its power, right? And then this one's A, and that's the number of electrons down there. Everybody okay with that? Fantastic. All right, so if we rearrange the Nernst equation to a form that contains the formal concentrations of A and B, formal concentrations, of course, being the amount that we believe there to be there, or the amount of all species there, right? We would get something that looks like this. So remember that you're going to have E, which is Nernst equation, equals an E0, but we've now separated some other terms out, okay? This would be things like this H plus concentration, right? See, we've separated that out. It's no longer in here. Okay. And we were left with the formal concentration of the product over the reactant to the power of its coefficient. These other terms here, when this is pH 7, this entire term in blue, the E0 plus the other stuff, this is going to be an E0 prime, okay? So the E0 prime has those other terms that we've taken out of here. at pH 7. Note if you're not pH 7 but not pH 0 either, then yeah, you would have a different value. You would not have an E naught prime. You'd have other terms here that you'd have to factor. By the way, why is it that pH 0 would give you an E naught? What's 10 to the negative 0? 1. 1 being unity, right? Okay. So this would be a monoprotic system here. So if we convert the A or B into the FA or FB, we would need a fractional composition equation. This will relate the formal concentration of all forms of an acid or base to its concentration in a particular form. Again, that would just be the normal fractional composition equation that you guys have gotten plenty of time to love and appreciate at this point. You guys have practiced a few times now, huh? So yeah, here's the monoprotic system. It looks just like you guys are used to, right? Notice the HA, there's the fractional composition right there, times the formal concentration. And that's what that equals. The H plus form times the fractional, which is that right there. The formal concentration over the H plus the Ka. And notice these are the exact same ones you saw in the acid-base systems before. You remember that a few chapters back where we had these? They're the exact same ones. There's no difference. This is for the diprotic system, by the way. Anybody have any questions on those? So let's find E naught prime for this reaction. So here we have dihydroascorbic acid. This is the oxidized form. This right here would be the reduced form. This is typically called vitamin C. So we have vitamin C, yay. Okay, so when vitamin C takes on 2 H pluses and 2 electrons, this will be the reduced form. That has an E naught value of 0.390 volts. But when we're talking about vitamin C, we probably are talking about some sort of physiological phenomenon. And that's definitely not happening at pH 0, is it? Okay. So what do we do with that? Well, we're going to first go ahead and abbreviate that. So we're just going to call that D, okay? Everybody okay with it? All right. And the ascorbic acid portion, the form of it with 2 hydrogens attached to it, is going to be the H2A. And then we'll rewrite it like so. Same reaction, just in a form that's easier to read. Okay? So we can write those symbols instead of these giant structures. So we go ahead and go through our steps again. We have a Nernst equation, E equals E naught, up there. It's for the 25 degrees Celsius. There's 2 electrons, products over reactants. Notice there's a 2 in front of that H plus, so it has to the power of 2, isn't it? And the water is pure liquid, so, unity. It's a 1. We don't have to list it, do we? So D, this is not an acid or a base, so its formal concentration is equal to its molar concentration. So the formal concentration of D is just the concentration D. That's it. For our diprotic acid, though, that is an acid. That's a diprotic acid, isn't it? The H2A, that's a diprotic acid. It has 2 H pluses it can give off. Notice this form right here is not a base because it requires 2 electrons to take those H pluses on. See that? A base doesn't require the electrons, does it? It can just take the H plus and has a positive charge. Okay? Do you see that this is not an acid-base reaction? Okay. So this is the equation for a diprotic acid. I'll be honest, you can derive this equation. I have derived this equation. When I took this class, I did not go to class for 70% of my lectures and got a warning halfway through the semester that I had to show up to all the rest of them or I'd fail. And then I aced all the tests. I actually got an A. But I didn't memorize anything, so I had to spend the first 15 minutes of the exams deriving all these equations from their base constants and from their base terms, right? So I would not recommend that. I would recommend just memorizing those, 4 equations, 5 equations. You end up using them quite often. And then, at the beginning of a test, take a piece of scrap paper and write them down on the side. So you don't have to derive them every time. That actually hurt my head, I'll be honest. That was something, I had a terrible headache when I took the test. Missed a couple problems because of that. I wouldn't have normally. All right. Anyways, so this equation right here gives you that fraction that's in the H2A, right? And so you can substitute this equation here for that concentration of H2A right here. Okay? And that's what we're going to do. We're going to take that Nernst equation, and we're going to put that fractional composition of the H2A, that concentration of the H2A in, that we just grabbed here. Notice all these other terms are constants and formal concentrations in H pluses, right? Which is a form of pH. Okay, so we can rearrange this a bit to make our lives a little easier. And so the E would equal the E naught, your Nernst equation stuff. We leave this stuff on the bottom except for the formal concentrations. We go ahead and take those out and get them together. Notice that we end up canceling this H plus because of this stuff down here. See that? Okay. And we group that in. All right. Is everybody okay with that so far? Okay. Again, we have a pH. We're trying to figure out the E naught prime, right? For our pH 7. So pH 7 means the H plus concentration is, 10 to the negative 7, right? So we can plug that in. So we have that. K1, K2, well, these are both constants, right? So we can get that from the tables. And our E naught was given to us up here. So we have everything except for this term. But we don't need that term, do we? Because that's not part of an E naught prime. Remember that the E naught prime was E naught plus this other junk here. And so once we figure these out, we subtract those off of the E naught, we get our E naught prime. Our E naught prime ends up being 0.0262. Notice we never have to do anything with this. That's why we took the formal concentrations out on their own, is because that was never part of E naught prime, was it? Is everybody clear what we're using here? So remember that this is E naught prime. The formal concentrations here of the product and reactant, they're never part of E naught prime. They're not an E naught, right? All we need is the fraction. the normally alpha portion, right? Okay. All right, anybody have any questions on that? Okay. Okay, this is calculating formal potentials right here. So this would be your pHs from 0 to 14. This would be your formal potentials in voltage. And what you notice is that what happens is your formal potentials are going to go down as your pH increases. But this has a diminishing effect because this is a logarithmic scale, right? And so you get large differences when your pH is first going up. But your differences become smaller and smaller and smaller as your pH gets higher and higher and higher, right? So for example, the difference between an E naught and a pH 7 is quite large. See that? The difference between a pH 7 and a pH 10 is not that much. You have a diminished effect. By the way, voltage is kind of interesting and weird. Like one of the things about batteries is the further you bring them down, the more they have to discharge because their voltage starts going down, but it's not a linear scale. There's essentially a flat portion to that scale, flattish. So like if you bring your battery down on your phone only to 50% every time and then you charge it back up, that actually gives you much better performance. Or have you ever noticed that like the time it takes to go from 100% to 50% is a lot longer than it takes to go from 50 to 0? That's because your potential is going down. Your voltage is going down. And so the amount of work you can do is less and less and less per electron moved. Okay? But anyways, if you ever want to talk about it, it's kind of interesting stuff. So actually pretty drastic difference as you go.